Welcome to the GEOTOP-A seminar. Today's speaker is Nicholas Beaton, who is going to talk about lattice models of theta-shaped polymers. Take it away, Nick.
Okay, thanks, DeWitt. So thanks for the invitation. It's a pleasure to be able to talk in the seminar, uh, at early hour of the morning notwithstanding. So this is some work that's sort of been going on for a couple of years now. It's sort of been percolating now and then I get back to it. And so it's joint work with Aleks and James Gleeson, who was our master's student who sort of did some of this work, and then we've sort of picked it up after he finished and kept going with it. Okay, so if I go that way, that works. All right, yeah, I'll give a little bit of an introduction, although I imagine most people listening are pretty familiar with all the sort of what's going on with polymers and things like that, but I'll talk a little bit about motivation, and then I'll talk about the Monte Carlo methods that we're using here. And so some of these are new, they haven't been used before. And so part of this is just also kind of a test bed to see how we can get these things to work. And then I'll talk a little bit about some results we've got in 2 dimensions and 3 dimensions, and then some sort of work we're still doing, and then sort of potential other things that we could do later on as well. Okay, so introduction. All right. So probably everybody here knows what a self-avoiding walk is, but if you're not familiar, we're going to use some lattice. So for example, the picture on the left here is the self-avoiding walk on the square lattice, the two-dimensional square lattice. And this little thing on the right is something in the three-dimensional cubic lattice. I haven't drawn the lattice itself, I've only drawn the walk. And so what are we doing? We're taking a sequence of vertices on our lattice such that consecutive vertices in the sequence are adjacent on the lattice, and no vertex occurs more than once. So the self-avoiding thing means that a vertex does not occur more than once. And so it starts at some point and it sort of wanders around along the edges as if it were some kind of random walk, but it's not allowed to visit a vertex more than once. So this is a walk that starts over here and then sort of wanders around and comes over here. And this is a self-avoiding walk which starts up there at the top, and then the end point is buried somewhere inside there. I can't quite find it, but it's somewhere in there. Okay, and so since the lattice is going to be vertex transitive, it's an infinite lattice. If one self-avoiding walk is a translation of another, we're going to consider them to be the same. Equivalently, that just means that we're taking the initial vertex to be the origin. We just fix the initial vertex to be the origin. Okay, and so then for any given lattice, we can count the number of these things which take n steps. And so, for example, on the square lattice, there's one walk of length 0, there are 4 walks of length 1, and 12 of length 2, and so on. And so this is a sequence. This particular sequence we know up to, I think, 79 terms, but it's a computationally very difficult problem, and so it becomes very difficult to compute more and more terms. Okay, so that's a self-avoiding walk. So a self-avoiding polygon is a really similar idea. It's just going to be a closed loop on our lattice. And so, I mean, the picture basically just says what it is. So, for example, this is a self-avoiding polygon on the square lattice, and so it's just a closed loop. We can, if we like, think about it, we can think about it as a self-avoiding walk, which wanders around and then ends back next to where it started. And then we can sort of just add in that last little edge to join the end point to the start point, or you can just think of it as a closed loop. And again, we can count the number of these things of a given size, a given number of edges. And again, we'll count them up to translation. So if I have 2 polygons which are the same, just one is translated, then we really consider them to be the same thing. And again, we can count these things. And now, depending on the lattice, it may be that these things have to have an even size. So for example, on the square lattice, they have to have an even length, and that's just because the square lattice is a bipartite graph. Same on the cubic lattice. And so if we sort of write down the sequence of the number of these things of a given size, on a bipartite graph, we're going to have every second term being 0 because they can only occur at even size. On some other lattices, and so I'll also be talking here about the triangular lattice and the FCC lattice. Those ones are not bipartite, and so we can have polygons of odd size. And that will make a little bit of a difference later on when we're talking about theta graphs, because it sort of removes some parity effects, and so it sometimes makes the data a little bit easier to analyze if you're working on the triangular lattice or the FCC lattice or something which is not bipartite. They've been studied for many years, and I'll talk a little bit about some motivation in a sec. Thetas, and so there's a picture here of tadpoles. I'm not really going to be talking about tadpoles in this talk. I'll mostly just be focusing on thetas, although we do have some data for tadpoles as well. And so, but mostly I'm going to be talking about thetas. Okay, so if we think about a self-avoiding polygon as sort of a subgraph of the cubic lattice or the square lattice or something, then every vertex in that subgraph has degree 2. And so what we can do is we can start introducing vertices of degree 3 and then think about what kinds of shapes that we get. And so the simplest kinds of things that we can do is if we have 2 vertices of degree 3, then there's sort of a couple of different configurations we can have, but one of them is this thing that we're going to call a theta. And so we've got 2 vertices of degree 3, where I've highlighted them there in red. And I'm going to say that there are just 3, I'm going to call them arms. So there are 3 arms joining these 2 vertices of degree 3. So there's one here and another one, another short one in the middle, and then a longer one over here. Alternatively, I could have something where I've got maybe a vertex of degree 1 and a vertex of degree 3, and that would give me this thing called a tadpole, where I've got a loop and then a tail. And then in 2 dimensions, there's some sort of topology going on as well, because now I could also have the tail inside the head, and that gives me 2 very different things. In 3 dimensions, that doesn't make any sense, but in 2 dimensions, we can have that as well. Okay, so we can count the number of these things as well. We again count them up to translation, just like walks and polygons. And so on the square lattice, the shortest theta graph has size 7. And so if we count the number of these things, there are 2 of size 7, there are none of size 8, there are 12 of size 9. And then the sequence is actually sort of not monotone, at least at first. It actually goes up and down and up and down for a little bit, and then it eventually becomes monotone. And then if we wanted to count tadpoles, again, I'm not going to talk too much about tadpoles, but if we wanted to count the number of those things, we can. And so the shortest one has size 5, and then the sequence goes on like that. And I can't remember exactly how many terms we have of this sequence, but it's not very many. It doesn't go much beyond what's written there. Maybe another 5 or 10 terms. Okay. So, right, lattices. Okay, so the main lattices I'm going to be talking about are just these first 4 here. So the 2-dimensional square lattice, the 2-dimensional triangular lattice, and then in 3 dimensions we've got the cubic lattice, which of course looks like that, and then the FCC lattice. So FCC stands for face-centered cubic. And here every vertex has degree 12, so it's a little bit hard to see, but every vertex here, it turns out, has degree 12. And the vertices are at the same locations as the vertices over here. It's really every second vertex. And then everything has degree 12. This is the BCC lattice, the body-centered cubic lattice. Here, every vertex has degree 8. I'm not going to talk too much about this, but it is another sort of relevant 3-dimensional lattice as well. But I'm mostly just going to be talking about these 4 here. Right, and so, like I was saying, there's sort of this parity thing going on. So, because the square lattice and the cubic lattice are bipartite, if I think about a theta, if I go back up to my picture of a theta here, because the square lattice is bipartite, it turns out that if I fix two vertices at degree 3, then any path that goes from here to here must have the same parity. So here, all of the paths that go from here to here are of odd length. And so that means that when I construct this theta graph, all the three arms have to have the same parity. And that's why you get this sort of kind of oscillating sort of parity effects going on with this sequence here. On the triangular lattice, that's no longer the case. You can have arms of different parities. And so again, that sort of reduces some sort of fluctuations in the numbers, and so sometimes it makes these things simpler to study than these things. Even though this is a sort of more complicated looking lattice, the fact that it's not bipartite sometimes makes things simpler. Okay, so a little bit of motivation. Um, Self-avoiding walks and self-avoiding polygons, of course, are useful as models of polymers. And in fact, they were sort of originally introduced by chemists who were interested in understanding polymers. And so the conception for self-avoiding walks is usually credited to Paul Flory. And so he was interested in trying to come up with theoretical models of polymers. Um, and so, for example, here's some real world polymer molecules, and here's a very long self-avoiding walk on the square lattice that was generated by Nathan Clisby. And there's obviously similarities between these things. And so you can measure certain metric properties of real world polymers. And in certain circumstances, at least when they're dilute, then the metric properties of these things turn out to match up with the metric properties of self-avoiding walks pretty well. And so what's going on there is that because self-avoiding walks have this self-avoiding property, you can't have two vertices occupying the same point in space. That corresponds to the excluded volume principle for real-world polymers, where I can't have 2 points of a polymer lying on top of one another. And so self-avoiding walks and polygons and so on capture this excluded volume principle. And so they're a useful model of polymers. They're also an interesting thing to study in their own right, and they have connections to models in mathematical physics and probability theory, and they're just often just a really interesting thing to study. They have lots of sort of interesting, complicated properties. They're also a useful kind of test bed for computational algorithms. If you're trying to count the number of these things, or you're trying to simulate the number of these things, there's sort of this long history of people coming up with very clever algorithms to count them and to simulate them. And so there's sort of lots of reasons to study these things, independent of the fact that they are good models of polymers. Okay. So knots, of course, this is a topology seminar. You all know about knots. So real-world polymers can be knotted. So on the right, there is a picture of DNA, which is in the shape of a trefoil knot. And it turns out that if you take a sufficiently long polygon in 3 dimensions and you sample it uniformly at random, then with very high probability, it will not be the unknot. It will almost certainly be a non-trivial knot. And so this idea is often now called the Frisch-Wassermann-Delbrück conjecture. And so it's sort of more precise than that. We can say that the probability of being unknotted should decay exponentially as the length becomes large. And this can be phrased in lots of different ways depending on the model. The FWD conjecture was first proved by DeWitt, who's here today, and Stu Whittington for self-avoiding polygons on the cubic lattice. And their method used pattern theorems. I'm not going to be talking about pattern theorems here, but the method that they used was pattern theorems. And then it's subsequently been proved for a number of other models as well. Okay. So sort of the original reason that I was sort of interested in looking at this idea of thetas was motivated by this sort of idea, where we're wanting to understand what kind of shape does a random knot have? And so I've done lots of work with Chris Soteros and a number of other people where we've looked at random polygons in long tubes. And it turns out that if you take sort of a long, thin tube, then you can actually prove some things about what random knots tend to look like. And so I don't have a picture here, but they tend to be this sort of long, thin thing, and then the knot tends to be quite localized. And so you have sort of this string of sort of knotted bits that sort of lie along in a row like that. But if we're not in a tube, then it's sort of a little bit harder to understand exactly what's going on. And so sort of a general kind of schematic for what a large knot could look like are these two pictures on the top here. And so on the right, we've got a trefoil knot where, in some sense, the knotted part of this thing is quite localized. We can sort of look at it and see, okay, well, the knot is this little thing up the top here, and then the rest of it is this kind of big unknot looking thing. On the left, we've got something different where somehow the knotted part of this thing is dispersed around the whole thing. You can't sort of point to a specific part of the polygon and say, there's the knot. Instead, somehow the whole thing is the knot. And so there's sort of this question of saying, if I take a large random knot, what does it look like? Does it tend to look more like this, or does it tend to look more like that? Depending on what kind of probability distribution you're talking about. And then if we're talking about real world polymers, we might say if we've got a large piece of DNA which is knotted, does it tend to look like one picture or does it tend to look like the other picture? Okay, so there's different ways of trying to get your hands on how do we measure this thing. And so a couple of different ways that were looked at 20 or so years ago were this idea of taking a large polygon and sort of picking 2 points. So, we've taken a large polygon and we've picked 2 points and we've cut it in those 2 pieces and we've thrown away one half. And we've taken these 2 pieces and we've somehow joined them together very far away. So that's sort of what this picture is trying to show, that we've thrown away this bit and we're left with just this thing at the bottom. And A and B, we're going to join together, but we're going to join them together by sort of very long things that go far away. And then you say, well, if this original thing was a trefoil knot, say, you do this for all different possible values of A and B, and you ask, for which ones do we get the same knot type as this? And so in this picture, we do, this thing is a trefoil knot. And if we cut it at these 2 points, we sort of join them far away and we again get a trefoil knot. And so in some sense, we can say that the trefoil must have been located in this segment here, and all this other stuff around here didn't contribute to the knot. And so that gives us some handle on saying, all right, well, the knotted bit was this bit here. How big was it compared to the overall polygon? And that gives us some idea of, well, did the original thing look like this or did it look like that? There's another way of doing this as well, where you take a large polygon and you sort of draw a very tight little loop about it in such a way that any knotted part cannot pass through the loop. And then you let the thing relax and you look at what do you get on one side or the other. So in this paper in 2005, these authors did this work and they came up with the conclusion that if I take a large prime knot and it's of size n, and I want to say how big is the knotted component, the number that they came up with was something like n to the 3/4, roughly, n to the 0.75. And so then, having known about this and then seeing something about thetas, which I'll show you a bit more in a sec, I sort of was thinking about, well, could we do the same kinds of thing for a theta graph? Can I take a theta graph and can I ask, well, does the average theta graph tend to look like this, where somehow the 2 vertices of degree 3 are sort of far apart and the whole thing is sort of dispersed among these 3 edges sort of roughly equally? Or does the average theta graph tend to look more like this, where I've got 2 little arms that are quite short and one arm which is quite long, And if it's this picture, well, how big does this bit end up being? How does it compare to this picture up here? So that was sort of the original motivation. There's also some biological motivations. So there's these things called R loops, which is this structure that occurs when you've got double-stranded DNA and a single-stranded DNA comes in and during replication, and so it sort of splits these two strands of the double DNA, excuse me, apart. And so while this is happening, you've got these sort of three strands going on, which is a little bit like a theta graph in some sense. And so you've got some sort of single-stranded piece and then another double-stranded piece, and then the single-stranded piece is going to be more flexible than the double-stranded piece. And so maybe you can put these things together and try and model this using a theta graph. And so this is an idea which I've spoken about with Marielle and other people. Unfortunately, we've never really gotten anywhere with it yet, but it's another sort of idea of trying to model something like an R loop using one of these three-stranded theta graph type shapes. And then the other thing is, sorry, that's just R loops again, is we can take one of these thetas and then we can put knots in it as well. And so you've got this idea of a prime knotted theta graph. And so here's just a few pictures. And so again, you can have a table just like we can have a table of prime knots. We can have a table of prime theta graphs, prime theta knotted theta graphs. And then there's questions like, well, for a given knot type, if I put it on, say, the cubic lattice, what's the minimum number of edges? And that's generally an open question. Maybe for a couple of these it's known, but otherwise it's mostly an open question. Okay. So right, so the Monte Carlo methods. Okay, so what I'm going to be doing is mostly using something called the BFACF algorithm. So the BFACF algorithm is named after those five people there. And so I want to be ultimately I want to be sampling these theta graphs and try and understand what kind of shape do they tend to take. And so the way we're going to do it is we're going to use this BFACF thing. And so the idea is that it's a model for or it's a method for sampling self-avoiding walks and polygons, which preserves topology. And so it does that by performing very small local moves. It's not like the pivot algorithm, if you know what that is, where I take a self-avoiding walk and I move a very large chunk of it, or I do a polygon, or again, I take sort of a large piece of it and I perform some sort of symmetry move on the lattice. Those are very good, and so that picture that I showed a few slides ago of Nathan, where he generated a walk of length 2 to the 25, that was done using the pivot algorithm. And so it's very good for sampling very large objects, but it's not good at preserving topology. And so if I'm doing something with, say, a polygon and I do a pivot move, I'm not guaranteed to have the same topology after doing the move. I could start off with a trefoil and then do a move and then get an unknot. It doesn't preserve topology. So we can instead use the BFACF algorithm, which does preserve topology. And so on the square lattice, there are two types of moves. So they're just these two illustrated here. And so what I can do is if I've got some edges of a polygon or a walk, and I've got an edge here, and I look at sort of the square that's adjacent to that edge. And now if the two vertices on the square, which are over here, are unoccupied, then I can take this edge here and I can bump it out and I get something like this. And so that increases the length of the thing by 2. I've gone from one edge here to 3 edges here, so I've increased it by 2. Or I could do the reverse. So if I have this sort of configuration in a walk or a polygon, I can sort of bump this square down and I start from this and I get back to here. The other type of move I can do is this neutral move where I've got this L bend here and this vertex is unoccupied, and I can just invert these two edges and I get this instead. So this is what it looks like on the square lattice. On the cubic lattice, it's exactly the same. There's just sort of more squares adjacent to each edge. Um, but otherwise, the moves are exactly the same. For the triangular lattice, it's even simpler. There's only one move and it's inverse. And all I have to do is just look for an edge and then look at the adjacent vertex. And if it's unoccupied, I can just bump out that edge and I get this. Or I can do the reverse. If I've got this bend here, I can sort of shrink it back down to a single edge. So now it's known that in 2 dimensions, for self-avoiding polygons, this algorithm is ergodic, which is to say that I can get from any polygon to any other polygon via a sequence of these moves. In 3 dimensions, that's not true because these things preserve topology. And so I've now got this sort of set of ergodicity classes where the ergodicity classes are exactly the knot types. So I can get from any unknot to any other unknot. I can get from any figure eight to any other figure eight. I can get from any right-handed trefoil to any other right-handed trefoil, and so on. So um, it preserves topology, but within a given topology, I can get from any polygon to any other polygon. Okay, so let me go this way. Um, so that's in 2 dimensions. In 3 dimensions, we've got the one on the square lattice just completely generalizes to the cubic lattice. For the FCC lattice, the moves look just like the triangular lattice as well. So for each edge is adjacent to 4 triangular plaquettes, and so you just pick one and do the move. For the BCC lattice, which I'm not really talking about here, it turns out there's 2 different types of moves, and they're kind of ugly, but it's been shown that if you implement both these types of moves, then you are ergodic in your knot types as well. Okay. So for trefoils, things are a bit more complicated because now we've got these vertices of degree 3. And so what we really want to be able to do is move those vertices of degree 3 around. I don't want to have them just fixed in place. That sort of defeats the purpose of the algorithm. I really want to be able to move them around so I can change the lengths of the 3 arms and so on. So it turns out that a few years ago, Tamaki, who was a master's student of Koya Shimakawa, found a set of moves on the square lattice or the cubic lattice which can accommodate vertices of degree 3. And so we've got the ones sort of these moves here and these moves here are exactly the same as the ones for just the regular polygons or walks. But now we've got all these other moves which deal with the vertices of degree 3. And so these ones here and these ones down here are basically just what you expect. If I've got a vertex of degree 3, sometimes I do a move near that vertex, but the vertex doesn't move. It's really these 3 here in the middle, which are the very interesting ones because they move these vertices of degree 3. And so in this configuration, when those 2 vertices are right next to each other, and I've got a plaquette like this, then I can slide that edge along. And so that's a neutral move. It doesn't change the length. But now here, I've also got this move here, which shifts one vertex a degree 3 along, or I can do the same thing when there's another vertex like there. And so now we've got this set of moves which can sort of shift around these vertices a degree 3. And these moves are enough to realize any ambient isotopic transformation. So now again, I've got in 3 dimensions, I've got these ergodicity classes, and the ergodicity classes are now the knotted spatial graph types. And I can, with these pictures, I've only got 1 or 2 vertices of degree 3, but in fact, these moves can accommodate any number of vertices of degree 3. You can always shift them around and sort of, so you don't have to have just a theta graph. You could have something with lots and lots of complicated edges. As long as everything is of degree 3, you can all sort of shift those vertices around. If you've got a vertex of degree 4 or higher, then things become much harder because then it's much harder to try and shift something like that around. But vertices at degree 3 at least can be shifted around like this. Okay, so for the triangular, oh, sorry, I'll give just a quick illustration. So here's a theta graph. I could highlight that square and then do a move like that, and that's effectively just a regular move as if it were a polygon. I haven't shifted any vertices at degree 3. But on the other hand, I could instead pick this square down here, and if I do a move there, then that vertex is going to move. And so I can, yeah, that's just sort of a little illustration showing that I can shift these vertices around. Okay, so for the triangular lattice, um, as far as I can tell, there are 3 different types of moves. Um, well, I mean, so the one at the top left is effectively just the same that we've seen before. It can take a vertex. It's just a bumping out of an edge, and so it doesn't matter whether we've got vertices at degree 3 or not. But now we've got these other moves here where now I can move around vertices at degree 3, and so this one has this sort of triple of configurations where I'm sort of rotating something around a triangle. And then this is a pair of moves here as well, where I'm taking this vertex of degree 3 and it's moving along here. And as far as I know, this set of moves is sufficient for the triangular lattice or the FCC lattice. I don't have a proof that it's true, but as far as I can tell, this set of moves works. And so for the time being, we're going to assume that it does in fact realize any ambient isotropic transformation. And then on the FCC lattice, it's just the same because all the faces are just triangles again. So it's just the same set of moves again. Okay, so the BFACF is this set of moves which takes a polygon and transforms it into another polygon, or a theta and transforms it into another theta. But usually the way we do these things is that set of moves is then embedded inside some algorithm which assigns a probability to doing a move. And so there's lots of different types of algorithms. Um, the one that I'm going to be using here is the Wang-Landau method. And so the Wang-Landau method is basically a method which is trying to sample, in some sense, uniformly across a set of states. It's been known for a while. It's used a lot in mathematical physics and statistical mechanics. As far as I know, it's never been used specifically for self-avoiding walks or polygons or these types of things. But it's actually it's quite nice. It's very easy to code up. It's simpler than some other algorithms like GAS or PERM or GARM, which have been used before for polygons and walks and things. You don't need to keep track of quite so much information. And so what we're doing is we're trying to come up with an estimate of the number of thetas of a given size, or maybe the number of thetas of a given size, and say we want to keep track of the shortest of the 3 arms. So I've got these 3 arms joining these these 2 vertices at degree 3, and I want to keep track of the shortest one of those. And so I want to come up with an approximate count for these things. And so this method is going to give me approximately how many configurations there are of a given size. And so roughly the way it works is here, you don't have to worry too much about the details, but what we're doing is we're taking a configuration, we're going to pick a random edge and a random square that's adjacent to that edge, or a random triangle that's adjacent to that edge. And we're going to ask, is there a valid BFACF move on that triangle? And so suppose we started with some configuration gamma, and if we did that move, we would end up with a new configuration gamma prime. And then we want to know what's the probability of accepting that. We're going to just use a metropolis probability. So the one that we're going to use is going to be the minimum of 1 and this thing here. So G is initially just going to be an array, which starts off as 0, but then we're going to update it as we go. And then these W's are just sort of the probability that a random move on my configuration would have changed gamma to gamma prime or gamma prime to gamma. So yeah, you can compute that by just knowing how big is your thing, how many edges does it have, what's the probability that I chose this edge, and so on. So this is just sort of a metropolis type probability. And so I compute this thing and I accept it with this given probability. And so either I accept it or I reject it. And suppose now I'm in state gamma double prime, which could be either gamma prime if I accepted the move or gamma if I rejected the move. And so either way, I'm in some new state. Now I'm going to take my G array at indexed by the size of the thing, and I'm going to increment its value by f, where f is initially just a number 1. And h is a histogram, and that's always just going to be incremented by 1. And I do this a bunch of times. I do this over and over again. And every so often, I look at h, and I ask, how flat is h? So typically, you would look at something like the biggest value in h divided by the smallest value of h, and you look at the ratio of those two things, and if that ratio is sufficiently close to 1, then you say that your histogram is pretty flat. I've sampled sort of all sizes pretty much the same number of times, so my histogram is pretty flat. And so if that's the case, I take my f value, which was initially 1, and I decrease it. And so typically what you're going to be doing is you're going to be decreasing it by some ratio. So I could take f and I divide it by 2. And I take my histogram, I reset it, I set the histogram down to 0, but I don't reset G. G still stays what it was. And then I start again, and I do this again. And so crucially, these metropolis probabilities depend on G. And so G is changing over and over and over as we go. And H, we check for flatness of H, and then once it's flat, we reset H, we decrease F, and then we go again and again and again. And then eventually f gets pretty small, and once it reaches some threshold, we stop. And then what do we end up with? It turns out that from this, you can show that the g's, or at least the relative values of the g's, give you these approximate counts. And so, or in fact, they give the logarithms of the counts. And so what do? I say, well, suppose I've got some known value, which could be the smallest configuration. I know how many polygons there are of size 4, or I know how many thetas there are of size 7 or something. I call that number little g, and I compute these values. What is AM? AM, that's a typo, sorry. There's no AM there, I think. That is possible. Oh, no, sorry, that's what I want. I just want to rescale all values by the number of polygons of size m, or the number of thetas of size m, where m is the smallest configuration. Then your approximate counts are what you get out of doing this calculation. Okay. And so you can generalize this thing where I'm counting, say, thetas by the number of edges and the length of the shortest arm, and so on. You can have a multi-dimensional histogram, and you do the same sort of thing. You can be fancy with how you change f. I won't worry too much about how I'm doing that, but you can sort of be clever about how you're changing f in order to try and minimize errors and so on. Okay, so now onto some results. All right. So just as a quick little test case, we might want to count the number of polygons. We know the number of polygons up to a reasonably large size. So that gives us sort of a kind of a good test bed. In 2 dimensions, we expect that the number of polygons, or in 2 or 3 dimensions, the number of polygons scales like this, where mu is some number, it's the connective constant, which depends on the lattice. So on the triangular lattice, it looks like this. On the FCC lattice, it looks like this. And G is an exponent, which in 2 dimensions is expected to be -5/2, and in 3 dimensions it's some other number. We're not sure, but we have a good estimate. And so we can use this BFACF algorithm with Wang-Landau to estimate the number of polygons. And what we're really looking for is this exponent. So I'm not interested in the connective constant. We know what that is to a very high precision. I'm really interested in saying I want to compare my numerics to what we expect and see if we get the same exponent. And so the way I'm doing that here is I'm taking my estimates, I'm taking the log of that number, I'm subtracting away the exponential part, and I'm plotting this against log n. And what I would hope to have is a straight line where the slope is that exponent. And so here this is the data, and I fit it to a straight line, and we can see that the slope of the straight line is very, very close to -5/2, which is what we want. So the algorithm does seem to work pretty well, at least for polygons. Okay, so then on to thetas. So in the first instance, we might just want to count these things. And so we might say that the number of thetas should grow similarly. So it should have some constant factor. We should have the exponential growth rate where the mu is the same as it was for polygons. It's the connective constant of the lattice. And we've got some power law, which is n to the h for some value of h. And so what I really want to do is estimate this h. And so the way I'm doing it here is I'm not plotting it against log n. I'm doing a similar sort of thing, but I'm plotting it against 1 on log n. And then what I want to do is I want to try and extrapolate these values. As n becomes large, they're going to approach the axis here, the y-axis. And I'm interested in where I expect this thing to be intersecting the x-axis. Sorry, the y-axis. And so the dots here are my estimates from the computations. I've done 10 independent runs up to size 500. And I'm trying to fit this to a curve where I would expect the curve to be something like this. This term on the right here is some sort of correction term, which I'm not quite sure what it is. So I'm guessing it's either of this form or this form. And what I'm interested in is what the intercept here is, which is these constant values here. And so depending on what we expect this lower order term to be, we get either something that's very close to -3/2 or something that's a little bit bigger than that. And now, if it is indeed this -3/2, and I think this is more plausible than this because I think this is a better fit than this one. What does that mean? It means that this exponent h is 1 greater than it was for polygons. For polygons, we had -5/2. For thetas, it looks like we're getting -3/2. And that makes sense because it makes sense if my average picture of a theta is a big loop with a little tiny loop inserted inside. I've got my 2 vertices at degree 3 and they're quite close together. I've got 2 little short arms joining them and then 1 big long thing elsewhere, because the idea is now that I've got sort of a big polygon with a little thing inserted inside. And if my big thing is of size n, then I'm going to have on the order of n places to put the little thing inside the big thing. And so I should have an extra factor of n, which is to say I increase my exponent by 1, and hence the exponent here is 1 bigger than it was for polygons. And the data does seem to be bearing that out, I think. So it seems pretty likely, I think, that this exponent is 1 more than it was for polygons. And I'll have a look at this data again in 3 dimensions in a sec. So this is for the triangular lattice. We can do a similar sort of thing for the square lattice. And we get a similar sort of picture. It's a little bit messier. The square lattice, because it's a bipartite graph, I've got this sequence of odd values and the sequence of even values. So I have sort of 2 different things I have to extrapolate against. But again, depending on exactly what your correction to scaling is, it again very much looks like -3/2. So again, one more than it was for polygons. Okay, so that's the number of thetas. We can also, oh, where are we? Here. We can also now look at the shortest arm. So I've got a theta, it's got a given size, and I'm also keeping track of the shortest arm that's joining these two vertices at degree 3, and I'm interested in how is this thing scaling on average. And so um, I'm going to say sigma for a given theta. Sigma is going to be the length of that shortest arm, and I want to average that over all thetas, and I want to understand how is that behaving. And so this is a similar sort of plot. Again, I'm interested in where this thing is intersecting the y-axis, and I'm using a couple of different types of fits depending on what the correction to scaling is. And so again, I'm interested in this constant term here. That's giving me an estimate of this exponent here. I'm saying if I expect the size of the shortest arm to have a power law behavior, just like that numerical work earlier on looking at prime knots, and they were interested in the size of the knotted component. I'm doing a similar sort of thing here. I'm interested in the size of the shortest arm as a proxy for the size of the kind of little loop inside the big loop. And so if we expect that thing to also have a power law, then I'm trying to estimate the exponent here, and we're getting something around about 0.57, 0.58, 0.59 in 2 dimensions. This is still in 2 dimensions. So that's for the triangular lattice. We can do a similar sort of thing for the square lattice. And we're getting a similar sort of exponent out, somewhere about 0.57 or 0.58. We could also look at not the shortest arm, but the second shortest arm, or equivalently the second longest arm. And what do we get? We get probably the same exponent. Um, and so that makes sense because if I've got a little loop that's embedded in a big loop, then you've got two little short arms and one long big arm. Well, you would expect the two short arms to roughly be the same size. And so you would expect the exponent for those two things to probably be the same. And the data does seem to bear that out, that it is probably the same exponent. So that's the triangular lattice. And then the square lattice, yeah, the square lattice is a little bit messier. The data is a little bit sort of all over the place depending on what correction to scaling you're trying to fit it against. But I did say it's very likely, again, about the same thing, about 0.58, 0.59 or so. What is this? So this is just, okay, just plotting the ratio of those two quantities. We would expect that to approach a constant. If they have the same exponent, they should approach a constant. And that does seem to be borne out. So that's the triangular lattice, and that's the square lattice. And you might wonder if that ratio is universal. It might actually be the same ratio for all 2-dimensional lattices. And I think that probably is true, although I haven't done a really careful analysis of that. And I think lastly, yes, here's just some samples. So here's a random theta on the triangular lattice of size 200. We can see, again, I have one very long arm and two very short arms. If I like, I can force the three arms to all be the same size, and then I get sort of a shape that looks like that. Okay, so that's 2 dimensions. I'm mindful of the time. So now for 3 dimensions. So for 3 dimensions, we can again look at the number of thetas. And so again, we might ask, is the exponent for thetas one bigger than it was for polygons? So remember, for polygons, the exponent is something like negative 2.76. And if I count thetas and I look for the exponent now in the number of thetas, then I'm interested in where this is intersecting. And depending on the fit, we're probably getting something that's about the same. It's a little bit messier, but I would strongly suspect it's probably the same exponent again. So it's the exponent for polygons plus 1 again. Should be mindful, of course, that what I'm sampling here are unknotted thetas. So I could also be sampling thetas where maybe one of the arms has a trefoil knot in it. I'm not doing that here. All the arms are individually unknotted. Technically, that means that I'm using the wrong growth rate. This is the connective constant for all polygons or all walks. Really, I should be using the growth rate for unknotted polygons, but A, I don't have a really good estimate for that, and B, it would be very close to the one for all polygons anyway. It's probably the data is not going to bear that out anyway. Okay, so we probably get that exponent. That's the square lattice. This is the cubic lattice, probably the same exponent. And then what we're really here to see now is this. We're really here to see the mean length of the shortest arm. Does this have any connection with the size of a small trefoil knot or the size of a small figure-8 knot or something? And so we look for the mean length of the shortest arm in a three-dimensional theta. And depending on the fit, and again, I think this one is a better fit than this one. We are getting an exponent that is indeed pretty close to 3/4. It's maybe a little bit bigger, maybe a little bit smaller, but it's certainly in the ballpark of about 0.75 again. So that's for the FCC lattice. I can also do the cubic lattice. Again, it's bipartite, so I've got these two different odd and even sequences. The data's quite messy, but again, everything is around the ballpark of about 0.75 again. So yeah, probably that would, if I had to guess, I would say that's probably about the exponent, roughly in that number. Um, we can look at the second shortest arm. The data gets a bit messy, but we're probably getting the same exponent again, like we would expect. Um, and then for the cubic lattice, we get that as well. And then we can look at those ratios again, and we get, again, probably the same value coming out. And I will skip that for now because I'm about to run out of time. But here's just a couple of samples. So here's a random theta graph on the FCC lattice of length 120. And so we can see here we've got one very short arm, one that's a bit longer, and then one that's much, much longer. And I can again force them to all have the same length if I like. And if I do that, I get kind of a bit of a big mess. But my vertices are degree 3, one of them is there, and the other one is up here. And this should be, yeah, all three arms should have the same length. So it should be 40, 40, 40. Right. Okay. So yeah, keeping on the time. Yeah, so sort of other ongoing and future work. So we do have some data for tadpoles as well. Tadpoles where the tail is outside of the head are not really that interesting because what we seem to be seeing is that the head is usually extremely small and the whole thing basically just looks like a long self-avoiding walk with a tiny little loop on the end. Possibly the loop is on average constant size. It doesn't even increase with size. It just sort of approaches a constant. When you're in 2 dimensions and the tail is inside the head, then that's much more complicated and the data is much harder to analyze there. You can also do thetas with all three arms forced to be of equal length. And then now we do have some predictions about what that exponent should be, at least in 2 dimensions, because that goes back to some work by Bertrand de Plantier, who has some predictions about if I have two vertices of sort of fixed degree and I have a number of arms joining the two things and all the arms are of equal length. So I think the word for that is monodisperse. Then he does have predictions about what those exponents are. And so we have a little bit of preliminary data trying to see if the data actually matches his predictions. And then you can do things like knots. And so in his thesis, James did a little bit of stuff where one of the arms was knotted, like he put a trefoil into one of the knots, into one of the arms, and then ran the algorithm on that and tried to understand if I have one of my arms containing a trefoil, does it tend to be the one that's much longer, or is it sometimes the case that the knot sort of gets pushed through a vertex of degree 3 and then the long arm is actually the unknotted one? So he's done some work on that, and that's still ongoing. And then, yeah, the other sort of applications that I talked about earlier, looking at prime theta knots or trying to model R loops or something like that. Anyway, I'm pretty much out of time, I think, so I better stop there. But otherwise, yeah, thanks.
Nick, thank you for a very interesting talk. The floor is now open for questions.
Hi, Chris.
Hi, very nice talk. Thank you. I have a couple of questions, maybe just about the last thing that you said there. So what do you think about where the knot's going to go? Is it going to be separate from the small sort of theta part?
Um, yes, on average, I would say very likely it is. We were sort of, yeah, I mean, James did a little bit of work, and we were sort of wondering, is it even really possible for the knot to move somewhere else? And it turns out it is. The knot can sort of relax a little bit, and then you can actually have a vertex of degree 3 that gets pushed through the knot. And so you have this sort of double-stranded thing that's sort of winding its way through the knot. So that can happen. Um, I'd say it's extremely rare, but it can happen. But yeah, on average, I would say it's much more likely that the knotted part is going to be sort of pushed away from the vertices of degree 3 a bit. Yeah.
And the other question I had is for the 3D, um, you showed length 400 as an example.
Hmm.
So how high lengths were you able to do? And is there how difficult would it be to go to higher lengths?
I can go to higher lengths, but the data gets worse and worse. It's
Uh-huh.
so I've gone to 400 there because I could sort of get a reasonable set of data. Um, yeah, I mean, sort of the algorithm, this Wang-Landau algorithm is trying to flatten over a histogram. And so if I'm measuring thetas by the length and by the size of the shortest arm, say, then the number of things in that histogram scales like n squared. And so you're trying to flatten over a histogram which is sort of size increasing quadratically. And if you want your data to be good, then you really need that histogram to be reasonably flat. And so it gets harder and harder. So yes, I could go bigger, but the data would not be great. And would I be able to like improve the quality of the estimates? Eh, maybe, maybe.
Yeah, it looks like hard work for sure. Thank you.
So, Nick, do you have pattern theorems that work for vertices greater than or equal to 3?
What are you trying to prove, I guess? So,
For sufficiently large things, you're going to see these patterns in your embedding.
so, right, okay. I mean, so I think that's not. I mean, in principle, I don't think that's really any more difficult than it should be for polygons. I mean, so you need to be able to do things like unfolding and stuff, maybe. I think in principle it should be doable, I think. The kind of thing where you would say, if I've got a pattern and it's a Keston pattern, so I know it occurs with very high probability lots of times in a polygon or a walk, um, you should be able to say the same thing for thetas. The proof is Yeah, it's a good question. I don't know. It's probably either straightforward or very difficult.
Impossible, yeah. Interesting.
Sorry.
May I?
Yeah.
Yeah, and Nick, very nice talk. I enjoyed your talk. The analogy that you had with the scaling of the knot size is very interesting and intriguing. So one aspect that I think is increasingly seen in simulations of lattice. So this is what we did and that group did. So I'm not sure, but I think that would translate also to on lattice for very large sizes. Is that if you look at the probability distribution of knot lengths, that has a modal value that seems to be very much independent of the chain. This is what with independent theoretical arguments, Shura Grossberg and Isaac Rabin have also argued about metastable knots. So a preferred and most probable knot size, independent of chain length. And then you have a rather slowly decaying tail that decays with a power law. So that what happens, if you look at the modal value, that is length independent. But if you do the average, then you pick up the contribution from the tail and it keeps increasing, no? And contributes to this power law, which of lattice data seems to suggest it is quite a bit smaller than 0.75, closer to 0.5. So in connection to with that, have you looked at the probability distribution of the length of the shortest arm? Is there a peak that shifts, or is it a modal value fixed and a tail?
So the answer is yes, indeed, I have. And so if we come back here, this is something I skipped over because I was running out of time.
Right.
But
So
if we
I
go
may
here,
have
that's
missed it,
exactly
so-
what this is. Yeah. So this is now something that definitely does not match what you were just talking about. So if we look at this is the distribution of the length of the shortest arm in 3 dimensions. And the green line is the average value. And indeed, we have something totally different. So I don't have a peak, a modal value, which sort of ends up being kind of independent of the size. We have something totally different. So the average, it's monotone decreasing, basically. So the distribution is totally different. So indeed, that mean is sort of increasing with some sort of power law, but the distribution looks totally different. So yeah, that's definitely a big contrast, and that's something that appears to be quite different. Yeah, these things, the modal value is basically the shortest value. Yeah.
Okay, thanks. Sorry if I missed it.
No. I skipped over it because I was running out of time. But yeah, Chris.
Can I answer DeWitt's question? So
Yes.
Please.
if it's fixed graph, if it's a fixed graph, we know that on the square or simple cubic lattice, that the growth rate for a fixed graph is the same as for walks. And so you can show based on that any pattern that would occur in a walk will occur in embeddings of the fixed graph. So for a theta graph, but if you, I don't know if you just allow any number of degree 3 vertices, I'm not sure what happens then. But if you fix the graph type, I think that.
Yeah. So if you allowed any number of vertices at degree 3, yeah, I mean, you have to, yeah, what exactly are you counting, I guess, is the question. If you, that's I mean, yeah, so then, I don't know. Maybe then you can prove, you might actually be able to prove that it's strictly greater, because now you might be able to show that, yeah, I've got some other kind of weird pattern, which is like a little thing.
Yeah,
where
it won't be the same as walks anymore, right? Yeah, for sure.
No, it's going to be something bigger. Yeah. It's going to look more like lattice trees or something. Yeah.
Okay, are there any other questions?
Well, I got a very basic question. It's about the BFACF algorithm. So on that part when you explain the algorithm So you mentioned that there is this set of moves that that you can use to create any possible theta graph, and in the sense of like topology types, right? But from what I understood, it hasn't been proved that these moves are sufficient, or it hasn't, or I wasn't sure.
So for the square lattice and the simple cubic lattice, it has been proved.
Okay.
So yeah, it has been proved that you can get from any fixed topology, for anything of a fixed topology to anything else of that same fixed topology. For these guys, it has not been proved.
Is it more complicated, or what is wrong with that specific case?
So if we go back to here, this thing. So so for the cubic, okay, so if we go back to polygons on the cubic lattice, the proof that the ergodicity classes were the knot types is essentially, roughly speaking, you're taking a polygon and you show that you can do some moves to kind of squish it down a bit, and then you show that you can perform all the Reidemeister moves. So that you've got a sequence of BFACF moves which can perform any Reidemeister move, and so that enables you to get from anything like that. For these guys now, so for the FCC lattice and the BFACF lattice, from memory, what they do is they basically take these lattices and they sort of inflate these things a bit. So they kind of move the vertices away, and then they push that thing onto the cubic lattice, and then they just use the existing proof for the cubic lattice.
Okay, I see.
For this stuff, I would expect that if there was a proof, it would probably be a similar sort of thing, that basically you would want to take this lattice and sort of inflate it a bit and then sort of shift things around until you can force it onto a cubic lattice, and then just use the proof for the cubic lattice is probably what I would be trying to do.
Okay. Okay, thank you very much. Well, probably this is more obvious to answer. Are these how you say minimum setup move? Is this a minimum setup move?
I believe so.
Okay, yeah, because
yes.
Okay, see.
Yeah, I think that if you take away one of these types of moves, then you won't be able to achieve everything. I think you need this set of moves. Yeah.
Yeah, you will miss like some Reidemeister's moves or something like that.
Yeah.
Okay. Well, thank you very much. Excellent talk. Thank you.
Okay, if there are no other questions, let's thank our speaker very much. Thank you, Nick.
Thank you.